We do have a quiz today, but it's unofficial, let's say.
No!
Quiz online.
Oh, really?
You guys can do it on your own. The answers are there.
Oh.
It's not going to count. Like, you can do it for yourself.
Wait, what? I don't know. I was going to ace this one. Yeah, this is the one.
This was the one.
Like 12:30 last night. I'm like, no way, I should send it out.
Yeah, that's why I came in, and it wasn't the usual conversation, like just everyone talking about nonsense. I hear people discussing DT versus DS's. I hear people, I see this guy's like, yeah, that's why. That's why I didn't. Anyway, do the quiz on your own. It's on the website, and there are instructions for how to do it. Would we
watch?
Class website, where all the quizzes are.
I remember the whole Laplace table.
You don't need to. Like, you don't need. I know it's not right. It's not gonna matter at this point.
There's no more quizzes.
No. So we just have a test next time. Last time on Wednesday. Yeah, Wednesday.
So wait.
So the last test is next Wednesday. Not this week Wednesday.
That's what.
The last class. The test is the last class. Anyway, last time we talked about something called the Laplace transform. Okay, right there. What was that?
F of s is equal to the function.
F of s
It's an integral, improper integral from 0 to infinity. F of t. Where x is negative natural log of x from 0 to 1.
Yeah. Right, you don't need to know that.
At least the answer.
Like, the one quiz everyone's prepared for. It's better late than never. We finally made it.
So wait. Question.
Anyway.
Professor?
Yes.
So, are you gonna grade it, or are you gonna give us like
No, not
100?
You do it on your own.
No, but like, are you gonna give us like a Thanksgiving 100?
No, don't.
Really?
That was the Laplace transform. And we also found that we could take the Laplace transform of derivatives. And we know that the Laplace transform of the nth derivative of a function is?
The n-1 derivative at x naught, y to the n-1. Negative.
What's the first derivative? Negative.
Evaluated at 0? No.
Plus Laplace of n plus
S times Laplace of the other one. So that's a nice recursive formula that you can use to figure out the Laplace transform of derivatives in terms of the Laplace transform of previous derivatives. Eventually the idea is you break this down to the Laplace transform of y, the original function, and use that as the variable that you want to solve for. There is a longer formula here, but even I never remember it because I don't like memorizing long formulas. But you could, for each derivative, it's s to the n, the Laplace transform of y, minus Sn minus 1 Sn minus 2, this is y of 0, Sn minus 2 times y minus 0. formula that you can actually memorize for all the guys going down. I never bother memorizing it because this is a lot shorter and you don't waste any time doing this for a second order. And essentially, it all started out looking innocent, and okay, that's neat, but then you realize that, whoa, we can use this to actually transform a differential equation into a polynomial equation. And, that's when things got real. And it was really cool. And because of how the formula is made up, we have our initial conditions kind of built in. So once we actually solve it, we don't need to worry about C1s and C2s and all that stuff. It'll all be built in. And basically, for Laplace transforms, you should know the definition. You should also know that top formula, that bottom formula. I don't even know if I had the right one. No, well, I wasn't right the first time. I think I sketched it down. That's the y0. Then it goes to y prime, and then it goes all the way down to the y to the n of 0 all the way down there. So you have the s to the nth power, and it counts down until it gets to the 0 power, and the y starts at the 0th derivative and counts up until it gets to the nth derivative. But I think the top one is fine. That's the one I always remember and I always use. But we got some examples. So let's actually get through these relatively quickly. And I believe this was one of them. And C, y double prime minus 2y prime plus 2y equals e to the minus t. And y of 0 equals 0, y prime of 0 equals 1. Now, I'm hoping that last example works out to something nice because it was just a random example I picked out of the book. Because someone asked the question, what happens if it's not homogeneous? So I just like, let me pick one. so we can deal with it together. Okay. So how do we deal with this?
Do you take the Laplace of each term?
Right. The idea is you're going to take the Laplace transform of both sides. Because the Laplace transform is an integral, it distributes across sums. So the Laplace transform of the left side is just the Laplace transform of this plus that, and then the Laplace transform of that. And then, so what's the first thing you do? You call your Laplace transform something, say big Y. Some people use big L, I'll use big Y. And then you find the Laplace transform of the others. So Laplace transform of Y prime?
Negative, positive 1.
Minus y0 plus s times the Laplace transform of y. That is going to be minus 1 plus s times big Y. Then you go to the Laplace transform of y double prime. This is going to be minus y prime of 0 plus s times the Laplace transform of y prime. This is going to be positive 1 plus s times this. That's minus s plus s squared 1. And then we plug these in. So we have y double prime, which is just this guy, 1 minus s. So the danger here with the s is that you might mistake it for a 5. So be very careful. Minus y prime, so it's the negative of this. Plus 1 minus sy, minus 6y, so it's just that, equals 0. The Laplace transform of 0 is going to be 0 just by plugging into that formula. And so now basically you solve for y. So This means that y, I can factor out a common y. And here I would have 1 plus 1, which is still 2. So I can move it over, and that's minus 2. And then I have the minus s, which I can move over, and it becomes positive s. And so my y is going to be s minus 2 over s squared minus s minus 6. And it turns out that's actually the answer. But it's not in a nice form. How do we put it in a nice form?
Factor.
Does the bottom factor?
Minus 3 plus 2?
Yes, it is.
Plus 2 minus 3.
S
Minus.
plus 2 times s minus 3. Like that.
The negative at the top. Or no?
Okay. What is this?
Oh.
You guys can use the table in that I gave you last time. I'll give you the table on my test. Which one does that look like?
E to the AT cosine B? Is it?
It looks like this.
EAT cosine
Yeah.
E to the AT cosine BT.
Yeah.
No.
That would look like s minus b s minus a over s minus a squared plus b squared, no?
You could just look at S.
So it's e to the AT cosine.
The denominator doesn't look like that.
Well, you could expand the denominator and then you could factor it in a different way. Because if you expand it to s squared minus 2as plus.
There's a nice way. It's not this.
Okay.
Yeah?
You can use partial fraction decomposition.
Partial fractions.
Oh my
Right? You don't do that thing if you can actually factor the denominator. That you do when you can't factor. Like if you can factor, that's when you come to this word. But this can be factored, which means you can do a partial fractions. So we're going to do the partial fractions for this. S equals minus 2 makes that 0, so I'm going to cover that up and plug in minus 2. That will give me minus 4 or minus 5, that's 4 and 5. And s equals 3 makes that 0, so I'm going to cover that up and plug in s equals 3, that's 1 and 5. So that's the partial fractions. So this means that my original y of t is going to be, now that should look like someone.
E to the AT.
So this is
E to the negative 2t.
e to the minus 2t. What happened to the forfeit?
You divide. You shift it. No.
It's just like it's just
Factor.
right? It's an integral. You can factor a constant out, right? So this looks like 4 over 5 times 1 over s minus a minus 2. That is like an s minus a, right? So that's your exponential here. This here is of course e to the 3t, and then there's a 150 from it. You will notice that I now have the full answer, complete with the arbitrary constants actually filled in.
Professor?
And you can actually try this another way, like you know how to do that otherwise, right? You can just find the characteristic equation r squared minus r minus 6. You'd factor that. Of course, it'll factor into something like this. You would get that your e to the minus 2t and your e to the t, but you'll get a c1 and a c2 that you'll have to plug in those initial conditions in order to find them. Eventually, you'll get to the fact that there are forfeits in one.
We can also use a series to find A, right?
Series to find what?
To get the answer to A, right? Just use like a regular power series.
Sure, yeah. We can do tons of stuff at this point. It's just a matter of what's easier, or what would you ask for?
Good question.
Yeah.
So on a test, you're gonna tell us, oh, use this method to solve this equation, or we're just gonna use?
Well, yeah. I mean, if I'm gonna ask you something like to put a Laplace transform on a test, I'd force you to use the Laplace transform because otherwise you'd be able to go through the whole test and not do the Laplace transform, right? Because pretty much the kind of problems that I'm gonna ask you to do a Laplace transform for, they'd be easy for you to do by other methods. So yeah, I'm gonna require you to do the Laplace transform whenever I want you to. Yeah.
How did you get 4 over 5? Exactly.
I found the partial fractions. I did the partial fraction decomposition.
And then the cover up.
with the cover of it. I don't think that's officially what it's called, but but yeah, you kind of figure out, it only works for linear non-repeating factors, but you figure out what makes the denominator 0, you cover it up and plug in that number. So s minus 2 made this 0, so I covered that up and plugged in s minus equals minus 2 to get the 4/5.
I have a question.
Yeah.
Why are we always guaranteed linearly independent solutions when we use Laplace transformation?
Because we're solving a differential equation, we're guaranteed linear independent solutions for differential equations. Like this comes from the fact that it's a differential equation, so the solution has to obey the rules of the differential equation solution. Yeah.
So how did you jump from together e to the negative 2t, e to the 3t?
Because in that table,
Oh, okay.
you know that 1 over s minus a is e to the at. So that's what your original function looked like. This is what its Laplace transform will look like. So anything that looks like that is an exponential. So in this case, the s plus, this really looked like 4 over 5 times 1 over s minus a minus 2. So that's like my minus 2 is the a, and so it becomes the power of the exponential. So you don't have to memorize the table, but if you have the table, you need to know how to actually read it and use it. Let's actually do B. Didn't have to copy that, but set y equals Laplace transform of y. This means that the Laplace transform of y prime is going to be minus y of 0 plus s times Laplace transform of y. Minus y0. Y0 in this case is 2. S times big Y. And the Laplace transform of y double prime is going to be minus y prime of 0 plus s times the Laplace transform of y prime. Y of prime of 0 is minus 2, so this is plus 2. Plus s times this guy. That's minus 2s. Plus s squared plus 2. That becomes, I'm going to plug this into the differential equation. So it's 2 times y double prime. So I'm going to take that and multiply by 2. It's 4 minus 4s plus 2s squared y. Then 7 times y prime. So I'm going to take this and multiply by 7 minus 14 plus 7s y. Then I have 6y, which is replaced by big Y. So this is 6 big Y equals 0. And now I just want to solve for big Y. That's going to be 2s squared plus 7s plus 6. And I move everyone without a Y to the other side. So I already talked about that and that. So now I have minus 14 plus 4. So that's minus 10, and then I move it over here, so it becomes positive 10. Then I only have the minus 4s, which move it over here, it becomes positive 4s plus 2. And so my y here is 4s plus 10 over 2s squared plus 7s plus 6. Now that doesn't look like anything. First thing I'm going to try, does the denominator factor?
Yeah. Plus 4 and plus 3?
4 times 3 is minus 6.
Oh yeah.
Again?
Never mind.
You have a 2s squared, right? Which means you need a 2s and an s. And what are the numbers that will work here? 4 and 3. Where does the 4 go?
Hold on.
Now you need to equal 7.
Yeah, 3 and 2.
We can do that equals 7.
Yeah, but
Yeah,
it's
the
two
4s goes, the 4 goes with 2s.
Yes.
Oh,
Plus
okay.
two, plus three.
Yeah,
Plus 2 plus 3.
and,
4 can't go with the 2s.
why not?
1 and 3.
The 2 goes in the second parentheses, and the 3 will go in the
Oh yeah,
first.
2s
Yeah.
plus 3 and then it's s.
2s plus 3 minus s plus
Yeah.
S plus 4.
S plus 2.
S plus 2.
Okay, so we check this. So this would be 4s and 3s. How do we make sure that we get a 7? Well, plus and plus. One, I know that a 4 couldn't go here. Like, where was a 4 coming from in the first place? I don't know, because that's a 6. But a 4, a 4 couldn't go here, or the 2 couldn't go here, because if you put a 2 here, then 2 would be a common factor, which you'd be able to factor out. But if you could have factored out a 2, you would have been able to do that from the very beginning. So the 2 can't even go here. So that's how it factors. And so because that factors, that's another one that we can use partial fractions on. And gonna do that trick again. Or you can just do partial fractions the old way, there's nothing wrong with that. So you split that up into a over 2s plus 3 plus b over s plus 2. We multiply both sides by the denominator. And plug in convenient values of s or equate like coefficients of like powers. Either way, eventually you should be able to get to 2s plus 3 and s plus 2. What makes this 0? Well, s equals minus 3 over 2 would make that 0. So I'm going to cover that up and plug in minus 3 over 2. So that would become minus 6 plus 10 over minus 3 over 2. So that would be what? Minus a half. That's going to be the coefficient here. And s equals minus 2 makes this 0. So I'm going to cover that up and plug in minus 2. The denominator would become minus 1. The numerator would become positive 2. Right? What?
So that should be positive 1 now? It's minus 3 over 2 plus 1.
Minus 3 over 2 plus 2 is positive 1. And if I plug in minus 2 into the numerator, that's minus 8 plus 10, which is 2, over plug in minus 2 over there, that's minus 1. So that's the numerator here. So that would become
Minus 8.
positive 8, right?
Yeah.
This would just be minus 2. And well, this guy you should be able to see that easily. What about this guy? How do we do that?
Can you divide everything by 2? Can you divide each term by 2?
You can't divide each term by 2. You're changing the value. You can factor things out though.
You can factor 2 out.
So we can factor out the 8 over 2. We'd be left with s plus 3 over 2. Minus 2 over s plus 2. And so that would mean our y of t is equal to
8 over 2 e to the
8 over 2,
negative-
which is 4, e to the
negative 3 halves.
3 over 2t, and then minus 2e to the minus 2. That's your answer.
Why is that value negative again?
Which value?
The negative 3 over 2t?
Because the formula says s minus a.
Oh, okay.
So you have s plus 3 over 2, you have to write it as a minus 3 over 2. You have to make it fit with the formula in the table. So that's one. Now, let's get to the interesting, the non-homogeneous situation. Let's see how this works. All right, what do you guys think we should do?
Solve for the
And then particular.
Okay, Laplace transform both sides.
Yeah.
So for C, again, Laplace transform of y, call that big Y. Laplace transform of y prime minus y of 0 plus s times the Laplace transform of y. That is going to be 0. That's just s times big Y. The Laplace transform of y double prime is going to be minus y prime of 0 plus s times the Laplace transform of y prime. Minus y prime of 0 is minus 1 plus s times this, which is s squared y. And I would go and I would plug this in. So it's minus 1 plus s squared y minus 2 times y prime. So it's minus 2 times s big Y plus 2y. So it's plus 2y equals
1 over s plus 1.
1 over s plus 1. So now you see how you deal with the non-homogeneous case. You simply just find the Laplace transform of the right side. So before it was 0, now it's not 0 anymore. It's some other term. And again, you don't have to worry about solving the homogeneous first or blah, blah, blah. The Laplace transform has that all built in. You are going to get, if you have the two homogeneous solutions plus a particular, this will actually flush them all out.
Will this work if we don't have initial conditions?
Well, no, because you can't plug in this formula.
Could we still like keep that symbolic and then at the end still have undetermined coefficients?
You could, but your answer would be in terms of this.
Oh, okay, I see.
You still kind of like have a C1 and C2 built into the answer in that case. So you'd only be able to get a general solution. But this, when we actually plug in these values, it's finding this particular solution
Yeah, that's
all at once. Yeah, here, can factor out a y, we have s squared minus 2s plus 2. On that, I'll just add 1 to both sides, so this is going to be 1 plus 1 over s plus 1. So, our y here becomes, this is going to be s plus 2 over s plus 1 over, right, because I added this, over s squared minus 2s plus 2. Now, is that something nice? Does that factor?
got it.
That one's really scary. It's like flipping out. Does this actually factor?
Maybe distribute
You
it
could
as
check
plus 1
see
to
what
the
the
denominator.
quadratic formula.
Yeah, but s squared plus 2s plus 2, does that one factor?
Minus 2s plus 2.
That's
So this is s plus 2 over s plus 1 times s squared minus 2s plus 2. Doesn't factor?
yeah. Minus 1 minus 1.
It doesn't factor, right? So this one's a little bit harder. So we're still going to go through partial fractions. We're going to deal with the situation that doesn't factor pretty soon. But let's actually just go through and do the partial fractions. Can't do the trick here because this is a quadratic. So this is A. Let's see if you remember your partial fractions. What goes up here?
bx plus c.
Bx plus c. And Omar remembers his partial fractions. So what you're going to do is you multiply both sides by this denominator. You will get s plus 2 is equal to, multiply this, the s plus 1 will cancel. You get left with s squared minus 2s plus 2. And multiply this, those will cancel. You have bs plus c times s plus 1. And so,
Because it's linear.
Um,
the quadratic.
really, there are tons of ways you can proceed with this one from
Can we
here.
use equating coefficients to do it?
We can use equating coefficients.
The numerator.
So let's
let's
group them. We're gonna have some s squares over here. On the left side, what do we have? We have 0 s squares. We have 1 s, and we have 2 is the constant. On the right side, how many s squares do we have?
A squared.
We have as squared.
Yeah.
Plus
B,
Oh, and then
Plus
B
B.
C, yeah.
Right? This guy would actually be s squared. So that's plus b.
Minus 2.
minus 2a plus c
Plus D.
Plus b.
plus b. And how many constants do we have?
2a. Plus c.
Plus c. So what do we have here? So we equate coefficients. So the 0 must be equal to that. The 1 must be equal to that. And the 2 must be equal to that. So we will get a plus b equals 0. We have minus 2a plus b plus c equals 1. And we have 2a plus c equals 2. So what do we want to do here?
Solve for b, substitute, and then solve for c. And then solve for
So b here is equal to minus a. Once I actually find what a is, we can find the b right away. But what I'm going to do is I'm going to plug that in here. So that's going to mean minus 3a plus c is equal to 1. And here I have 2a, just copy this over, plus c equals 2. I can say, take this minus that. So I'm going to take the negative of this one and add them together. So this would be 5a. This minus that, the c's would go away, equals 1. So this means my a is 1/5. That also means that my b is minus 1/5. And it also means that the c, where's the c?
Don't
Well,
you get a
I can
negative
solve for
one?
anyone. What?
Don't you get a negative one for 5a equals negative 1?
No, I'm taking this minus that. So 2 minus a minus 3a is 5a.
Oh, okay.
C minus c, 2 minus 1.
Okay.
And then now 2 times a, which means 2 over 5, plus the c must be 2. So this means my c is going to be 2 minus 2 over 5. That's 10 over 5 minus 2 over 5, that's 8 over 5. So this guy becomes where were we? Back up here. So our big Y is equal to 1/5 over s plus 1. We already know what that's going to be. B is minus 1/5. So it's plus minus 1/5 s, and c is plus a over 5.
Okay.
All over s squared minus 2s plus 2. How do I figure out what this guy is?
Do you do division?
So at this point, the solution is already there, so it's just a matter of algebraic manipulation. Right? So here, notice that I could factor off this is 1/5 times 1 over s plus 1. I can factor off a negative 1/5. I would be left with what? S minus 8 over s squared minus 2s plus 2, which I would write as s minus 1 minus 7 over s squared minus 2s plus 2. Do you see why I wrote it like that?
Yeah. You're gonna break it up even more.
Huh?
So we can split the fraction up further.
Yeah.
Yeah, but why s minus 1? Why did I decide to get this specifically? What was wrong with the s minus 8?
Minus 1 is easier to work with the s squared minus 2s being
It's one of the charts.
If it doesn't factor, what are we going to do? Because nothing in our table looks like that.
No, you can't.
So what are the things in our table? What is the only other option?
Combine.
Right, we saw things with denominators s minus a. What other possible denominators were there? Because that can't happen here.
S minus a squared plus b squared.
S minus a squared plus b squared. Which means if I couldn't get that, that's what I'm going after. And which means I'm going to want to complete the square here. If I complete the square here, what's going to happen? That's s minus 1 all squared plus 1. So I saw that to complete the square, I'm going to get an s minus 1, which is why I want an s minus 1. So this guy here is, now I can actually split this up. So this is my 1/5 times 1 over s plus 1. This is going to be minus 1/5 times s minus 1 over s minus 1 squared plus 1 squared plus 7 over 5 times 1 over s minus 1 squared plus 1 squared. What's this?
E to the negative
E to the minus t. This?
Cosine.
e to the negative, or e to the positive 1t, and cosine.
And this?
Same thing.
That one's the sine.
Sine, yes. That,
Wait, how is
So
that a
that's our y of t. So here, as you can see, that's the part that comes from your homogeneous solution. Because had you done it the other way and did this would have a complex solution, right? Set that equal to 0, solve for s, you actually get a complex number. So that's where the cosine and sine comes from the homogeneous part. That part is who? That's your yp. Right? So this guy here is your yp. This guy here is your yh. Right? It all fleshes out.
is there always some kind of algebraic manipulation that can make you pick one?
Well, the interesting ones, yes.
Okay.
There's always going to be a way for you to finagle things. Like once you get with y equals something, that's your answer. The calculus is done. The differential equation is done. It's an algebra problem from that point on, right? So it's just up to you to figure out what algebraic technique am I going to use to kind of manipulate this to look like the things in the right side of the table. Right? So the good news is if things factor, just use partial fractions. If things don't factor, complete the square. And then try to make sure that the numerator plays nicely with the denominator, right?
Yeah, because it seems like those forms all kind of harken back into a technique that you would use to get there, right? Since like the s minus 1 squared plus 1 squared is a pretty obvious one, and then the one that we use for sine is also pretty obvious too. Like I don't know how you would get to that form without completing the square.
Yeah, so completing the square is the way I would go for this.
No, I just mean that like some of them I can see no way to get to that solution other than to do this.
Yeah, there's not going to be many options, and it's all going to kind of feel familiar because it's algebra. But that is that. So that's pretty much, I mean, for this class, that's the hardest it will get. Like you'll get that if I feel mean. Yeah, I'll show them. You know, everybody's having some kind of mood. I'll put an e to the minus t on the right side. But chances are something that you'll see on a test would be closer to one of those first 3 examples that I gave you. I might give you one where you have to complete the square, but I probably would make the algebra messy otherwise. But this one, yeah, I just randomly picked this and it was bad, but it was okay. It was alright. That's basically it for Laplace transforms. We aren't going to do any applications of that. You will do that in your other classes, like circuits. Laplace transforms will come back when you're doing circuits. Very useful there. So what we're actually going to do is jump to a whole other topic, which we're pretty much going to just introduce because we're not going to have enough time to do enough examples. So this is chapter 10. Technically, the main thing is 10.2, but I'll talk about some things that they would have spoken about in 10.1. And this is the idea of the Fourier series. Fourier, that's how it's pronounced. It's another one of those fancy things. Fourier? No, Fourier, that's how it's pronounced. Fourier series. So, here's the idea. Again, this is all sort of piggybacking on just how nice power series work. So, power series were really nice. They made a lot of problems a lot easier to solve. So, you might think, hey, maybe it's nice to have a continuous version of the power series. Something that doesn't work on discrete sums. Create the continuous version, you end up with a Laplace transform. Here's another idea that we want to use based on a power series, although not directly related to the power series, but in spirit it's directly related to the power series. The goal, express periodic functions. That's our goal. I saw a really cool YouTube video by 3 Blue 1 Brown. I don't know if you guys know. Where he did a series on Fourier series, and he literally used like a Fourier series to draw a picture of Gauss or something like that, which is crazy. So technically, you don't need to do with a periodic function, but we're going to do it with periodic functions because we are going to be using sines and cosines. Express periodic functions. Periodic function. Let's say it has period 2L, for no other reason than to make it nice in our computations. So we just think of the length as 2L, and as a series of sine and cosines. So, the need for power series arose because we wanted to do calculus, but some functions were just too complicated to do calculus with them directly. So, we were like, wouldn't it be nice if we could write this function as a polynomial? And the power series was born. Because polynomials are very nice, so if we can express functions as polynomials, it's really cool. Now, another set of functions that are very nice happen to be sines and cosines. In terms of periodic functions, these are the nicest ones we know about. So if I'm given some other periodic function, like a wave function of some sort, maybe it's describing some sort of melody, a radio wave, some sort of frequency that I care about, and it's periodic, how can I express it as a familiar function, i.e. sines and cosines? If we do that, we say we form a Fourier series. So f of x on an interval minus L to L is periodic. So it has some pattern, and let's say it goes like that. And what happens is it just repeats this pattern, right? So it just keeps doing that. But the length, the one principal period, I center it on the x-axis, so this is the xy axis. I center it, and I kind of do it so that the period, the center of the period lines up with the 0. So the length of one period is 2L, because it goes from minus L to L. So I have a function between minus L and to L that I want to copy that, going in both directions. And I want to be able to express this copy with sines and cosines. So, and the copy can look like anything. But,
are there holes between L and negative L?
Come again?
Are there holes at L and negative L? Because it's discontinuous, right?
Yeah, I'm going to talk about that a little bit later, because the Fourier series actually also deals with discontinuities very nicely. If your Fourier series hits a point of discontinuity, what it's going to do is it's going to fill in its own value, which is going to be the average of the two values. So if you have a point here and you have a point here, this is discontinuous, your Fourier series is going to fill in that middle point. And it'll literally just go from here, jump to this, and jump back up here.
Oh,
It will literally just, it will keep going. So if you wanted a Fourier series, how it will start to look like this, it will start to look like
Like a sawtooth wave?
Yeah, it looks like a sawtooth.
it is a sawtooth wave.
Yeah.
So the green is the actual function I care about, but the blue is my Fourier series approximation to that. And of course, the more terms I use, the smaller these things get, and they get very closer and closer to the line, to the point where I can make them exactly equal to within whatever tolerance I want. So that's the idea. Given this function, how do we get the blue wave? Right? The approximation to it. So let's actually just start by setting what we want. Set f of x equals to something like this. So we kind of make it look like a power series, but instead of a polynomial version, we want a sum of sines and cosines, where the coefficients of each sine and cosine are different. Now, we'll modify this to make calculations easier. So, that is not its final form, right? So that's the basic level 1. Now, we're going to start to modify this. One thing you'll notice is that if I plug in n equals 0, the sign is just going to die. So really the first term here, starting the series at 0, the first term for the sign doesn't actually matter. So one thing I can do is I can split this up, an cosine nx plus bn sine nx. Start this one at 1, start that one at 0. But now that doesn't really look nice, not very aesthetic. So what I'm going to do is I'm going to evaluate one term here, which is going to look like that. And so I can start both series at 1. So we have that. Now, this one, I want to write the constant term. So there's going to be a constant term that's separate from the series. I am going to write it as some other constant over 2. I'm just going to shift it. Put in a half factor for convenience. You'll see later on down the road when I start to derive certain things, there's going to be a factor of 2 that comes in here. Having that half there is going to cancel the factor of 2. It's going to look nicer. So whatever the actual number is, just think of it as some other number over 2. And here, I'm also going to modify this. You see, I want to make sure that the trig functions that I have here, the sine and the cosine, they must have period 2L. Right? By the way, what is the period of this function? What is the period of cosine nx?
2 pi over n.
2 pi over n, right? So if I want that to be 2L, what would I change the function to?
L
L over
pi, L over pi.
Because I want 2 pi over k to be 2L, right? I want the period to be 2L.
Pi over L.
So this means our k would be pi over L. So here I'm going to be pi x over L. Now that, however, is just one angle. I want to take multiples of these, so I change it to n pi x over L. So I'm going to have a 1 pi x over L, and a 2 pi x over L, and a 3 pi x over L. They'll all end up having here 2L. But I can get an infinite number of them. This allows me to change frequency. So sometimes I might want the sine or the cosine to oscillate faster or slower. So I'm going to choose the L that makes that work. So this is going to look like a n cosine n pi x over L is how I'm going to express the angle. And similarly, b sine of n pi x over L is how I'm going to express this angle. Right? So it's the same idea. I'm just kind of what we were doing with Laplace transforms earlier. I'm just doing some algebraic manipulations to make things look nicer. And that is the Fourier series. That's the final form. So this is called Fourier series of fx. So, i.e., you have found the Fourier series for a function if you can express it as a over 2 plus the summation n goes from 1 to infinity of a n cosine n pi x over L plus b n sine of n pi x over L. This is called the Fourier series expansion of the function. Now I'll mention a little bit about the convergence behavior of this thing later on, even though technically it's not really a part of our syllabus. But basically, when you want to find the Fourier series for a function, you need to express the function as that form, as the right side. What do we need to know to be able to express it as that?
L, A0.
Well, the L will be given. So, yes, you need to know the L, but that's kind of, I'm going to know what function I want to represent like that. So I'll know the period. In general, you want to find a power series. What is the most important thing for you to find?
A0.
The coefficients. The coefficients is what makes the power series, right? So, we need to find what must the A0 be for a particular function, what must the AN be, and what must the BN be. For a random function that you would choose to represent this way, how do you choose the coefficients? If you want to represent a random function as a Taylor series, we know how to choose the coefficients. F to the nth derivative evaluated at the point I care about divided by n factorial.
Well,
Are there equations for these guys? Yes, there are also equations for these guys. So, how do we go about finding them? To help, we need some pre-calc. You probably never did this in pre-calc, but it is something that if you learned it, you would have learned it at pre-calc, like this. It's one of those things. It's called the product to sum formulas. So that's the first thing we're going to need. We need two main things to make sense of these guys, but that's one of them. So you should know the addition formulas. For sine and cosine. Cosine of A plus B is equal to cosine A, cosine B, minus sine A, sine B. Cosine of A minus B is equal to cosine A, cosine B, plus sine A, sine B. Sine of A plus B is equal to sine A cosine B plus sine B cosine A, and sine of A minus B is equal to sine A cosine B minus sine B cosine A. Call this equation 1, equation 2, equation 3, equation 4. Now, here's something you can notice. If I were to add equations 1 and 2, these two guys will die. I'll get two of those guys added to these, and I can divide by 2 on both sides. So if I take 1 plus 2 and divide that by 2, I would get this equation. I would get cosine A cosine B can be expressed as 1/2 cosine A plus B plus cosine A minus B. This is called, it's a product to sum formula. I took a product of cosines and expressed it as a sum of cosines. It's called a product to sum formula. I can do the same for sine A sine B. Notice that if I take this one minus that one, this minus that, I would get 2 of these guys, so I can divide by 2 and get a half. So I take 2 minus 1 and divide that by 2. I would actually have here cosine of A minus B minus cosine of A plus B. That's another product of sum formulas. I can write a product of sines as a sum of cosines. The last one I want to know how to express is sine of A, say cosine of B. To figure out a sine A cosine B, I can add these two, right? These guys would die. I would have this, which I would divide by 2. So I would take 3 plus 4 all over 2. And then here I would have sine of A plus B plus sine of A minus B. So we have the product of sum formulas. I only need those 3. Why do I need that? I'll tell you why. I'm going to be required to find some integrals, which you're going to see pretty soon. The second thing is we need to know if I'm going to take a cosine of, say, nx times a cosine of some other constant, mx, and I want to integrate that from minus L to L, what would the result be? I'm going to derive one of these for you, and then I'm just going to tell you what the others are.
Break it up.
If I have a sine of nx times a sine of mx dx, what is that going to be? And if I have a sine of nx times a cosine of nx dx from minus L to L, what is that going to be? Let me show you how you look at the first one, and then I'll just tell you the answers for the others, because it will be simple. Notice that effect here, minus L to L. Cosine nx, cosine mx dx. How you do that is, you don't want to do integration by parts of that. It's going to be messy, and I don't think it's actually going to take you anywhere. You actually end up with like 0 equals 0 or something like that. It's one of those things that's impervious to integration by parts. So what is the option? What?
You express it in terms of one of the equations.
Yeah, that's why we need these guys. I'm going to use a product to sum formula. I can write cosine of A times cosine of B as that expression. So I'm going to write the 1/2 out here, and then I'm going to think of this as the A, that is the B. So this is going to be cosine of n plus m x. I'm not going to put the over L. Do I need the over L?
No.
Let's not worry about it. Plus cosine of n minus m x. Right? I'm really going to apply these integrals where the angles look like n pi x over L, but I think you'll be fine. So what is this going to actually look like? Well, now let's just, how do I integrate that?
Negative sine over nmx divided by n plus n.
Yep, divided by n plus n.
Divided by
N plus n.
n plus m.
Professor, isn't it positive sign?
It is positive sign. Who said negative sign? Plus sine of n minus m over n minus n. Some of them will give you zeros. I don't know if I want the L's in some of them. Let's see. Between that and that. I think I do want the L's. Let's do it with the L's. Let's do it with the angles I want. N pi x over L. 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 This is like our mantra, N pi x over L. You just keep saying that until you reach enlightenment. It'll happen. One day it's going to happen. Okay, so this would be pi x over L. Pi x over L. So when you reach the fourth ring, you just say pi x over L and it all works out. So this would be pi x over L. And then I'd have to end up multiplying by an L. And here I'm going to have to end up multiplying by an L. And here at n pi x over L. Okay.
Wait, why did you multiply by L?
Whoa.
Because L is a constant.
May it cancel out?
So I would have to multiply that over pi.
Okay.
So wait, they get canceled out or something?
Now it's inside the,
No, this n pi x over L is inside the angle.
Oh god.
But then by substitution, I take u equals this, du is going to be n plus n pi over L. Bring that to the other side, I'm going to have L over pi cancel. Okay. Now, actually plug in the L's, what's going to happen?
When?
Huh?
Yeah, it's hard to
There's
see where
no
to plug
X.
the L's in.
oh, there it is.
The L's go inside the x.
The X.
Oh.
The L's are going to cancel.
Yeah,
You're going to have sine of a constant times pi.
at 0, or,
That's going to be 0. Here, the L is going to cancel. You're going to have sine of a constant times x times pi. Right? So this is going to be 0. All that work for nothing. But wait,
That sucks.
We did all of that.
all of that for nothing. Yes, but almost nothing. There's not nothing. Because notice what happens here.
oh,
What would happen if m equals n?
Bad stuff.
Bad stuff. We end up divided by 0. So it's 0 if n is not equals to m. Right? If n equals m, what's going to happen?
0 or 0.
Well, so essentially, it will always give me, the integral is going to give me 0, except in one case. Whenever the n and the m coincide, something is going to happen. So, if n equals m, then I can't even get to this form in the first place. I'm going to go back, and I'm actually going to plug it in from the very beginning. And what's that? That's just cosine squared.
Then the m pi?
No, I'm assuming they're the same.
Oh,
Right? I would get 0 if they're not the same. If they're the same, I can't do this because I would divide by 0 here. So I go back to the beginning, make them the same from the very beginning, and I'm going to do it in another way. This is now just going to be cosine squared of n pi x over L. How would you actually integrate that?
is that 1 minus cosine?
Yeah.
1 minus 7.
Of 1 plus cosine of
You did the
2
negatives
n pi x over L. What is that going to be?
Good God.
Well, we can actually integrate that now.
Yeah, 1/2.
That will just be x. This is going to be, it's going to be plus L over 2n pi x
Sine.
times sine of n 2n pi x over L. Now, that's going to be plugged in between minus L and L. Now, obviously the sine part is again going to give you 0, but now,
Where did x come from?
The one we had triggered it.
No, on the, below the denominator for the L.
Oh, that shouldn't be there. Now the sign is going to give you 0, but notice now I have this guy. I'm going to plug in L, then minus, plug in a negative L.
That's L.
Actually get L. Wow. Another thing, if the m and n were the same, but there happened to be 0, we don't really have to worry about this case because our series starts at 1, but just in case you don't want to say I never told you about considering this. If it's actually 0, you would actually plug into this, you would get the minus L to the L of 1 dx, and that would again give you 2L. Right? So you can do this for all those two, and here's what you're going to do. These guys are piecewise functions, and this is something you have to be used to because with Fourier series you end up with piecewise functions very often. It will be 0 if your n is not equal to m. It is going to give you L if your n is equal to m, but they're not 0. It will give you 2L if your n is equal to m equals 0. You can do it with this, and you'll realize that it's going to give you 0 if they're not equal, and it will give you L if they are equal. You do this one, you'll get 0 in all cases. But that's what's going to save us. With this, we can now find the coefficients of the Fourier series.
Professor, what about
Huh?
0 for the second one?
If I put in 0 to the sine,
the
it
second
just
one?
gives 0.
If m and n equals 0?
Yeah, I would have 0 here.
No, for the second. Sine times sine. Oh no.
Anyway, you can derive the other one similarly. Let's just hurry up and get out of here. So, back to the Fourier series. Here's what we're going to do. I'm going to take that equation, integrate both sides from minus L to L.
How can we move the integral inside the summation sign?
Right, you have to talk about the convergence. It's actually going to be absolutely convergent.
How do you know?
That's in another section that we haven't spoken about. Just assume that we can actually do this. This is actually, it's absolutely convergent. There are other ways you can think about it because the series have n as the variable. Well, that's x, but never mind. So we can actually do that. Now, what is this? Well, what's the period of this?
L.
It's 2L periodic, right? I changed the angle to make sure the period is 2L. What's the length of the interval I'm integrating on?
2L.
2L. So what's the integral of a cosine if I'm integrating over its period? 0.
Wait, say that whole statement again? I'm sorry.
If you integrate a trig function over a full period, you always get 0 because there's going to be a positive part and a negative part.
Yeah.
The positive part of the cosine is going to cancel out all the negative parts. This is also going to be 0 for the same reason. So, ultimately, I would just have a0 over 2 from minus L to L dx
Which is
equals, minus L to L of f of x dx. What is this guy? This is going to be a0x over 2 between minus L and L, which is going to give me, plug in L is going to give me a0 times 2L over 2. This is why we put the over 2. Just to do that. So then, we're looking ahead, we're always into the future. Okay, now, what do you notice? I can actually solve for the a0. Divide both sides by L. That's how I find the a0 term. That's the a0 coefficient. Now we're going to use these to find the other ones.
So if we can't remember that, are we supposed
Oh,
to?
you have to remember this that I have in the box.
No way to derive it in the test like that.
No, you're not going to have to derive it. That's crazy. Okay, so now if I go back here, a0 over 2 plus the series and go from 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L. Here's what we're going to do. I am going to multiply both sides by cosine m pi x over L, 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 and then I'm going to integrate from minus L to L. Now, what is going to happen here? Well, that's going to be 0 because I'm integrating a cosine over its period. Cosine times sine
Is 0.
That's always 0. This guy, what's going to happen? He's going to be 0 for every term of the series except
M is equal to n.
when my n hits n.
Yeah.
My n is going to go 1, 2, 3, 4, 5, 6. Eventually it's going to hit n. Then it's going to continue. For everyone except when it's equal to m, they all go off to 0. In the case where it's equal to n, L is what's the result. So this just simply goes to L. And of course here I'm going to add that an because that's just a constant. From minus L to L. Now just solve for the an. Now because the m and n are equal in this situation, I can just replace the m with n. So this means that my an term is going to be 1 over L, integral from minus L to L, of f of x times this cosine n pi x over L. That's how I find the an term. Do this integral. Now, in a similar way, I'm not going to do it out, but I can multiply by the sine of m, as in Mark, n pi x over L on both sides, integrate. That part is going to give me 0. This part is going to give me L when the m and n coincide, and that part is going to give me 0 because I'm integrating over the period. So by a similar method, I can find the bn. And that's the Fourier series. That's how you find the coefficient. That's how you find everything. So what you need to know at the end of the day.
Are these 2 boxes?
Three boxes.
Pretty much everything I put in a box. So f of x is a 2L periodic function. then we may express it as f of x equals a0 over 2 plus the series n goes from 1 to infinity of an cosine n pi x over L plus bn sine n pi x over L, where the a0 is going to be 1 over L minus L to L f of x dx. The an is given by 1 over L, the integral from minus L to L, f of x cosine of n pi x. And the bn is given by 1 over L minus L to L, f of x sine n pi x.
So can we then just easily find entries, that any entry that we want in the series? Because this is n, right? We can just plug in different values of n to find out what we want.
This is going to be a series, like you're going to have a1 cosine, a2 cosine, a3 cosine counting up, b1 sine, b2 sine counting up. How do you find the a's and b's? These formulas.
Okay.
So this is actually going to give you a formula for an. Like when you do this integral, it's going to be a function of n. So when n equals 1, this is the first coefficient. When n equals 2, that's the second coefficient, and so on and so on.
Okay, so it's just like power series or anything like that, where
It's power series. This is the formula for the coefficients. So it's kind of like when you were finding a Taylor series, the formula was given by
so
the
this
nth
is like
derivative.
the end step of the power series stuff that we were doing before, but we're getting there faster.
Yeah.
Okay.
So this is actually just the formula that gives you the an. If you're doing a Fourier series.
Okay.
Is it that the only
Here it comes.
Huh?
Is it that the only reason we start the series at 1 is because we want to avoid the case where n is equal to m is equal to 0 is equal to 2l? We want to avoid that because you don't know if or whether or not that's true.
Well, technically, the 2L case would have factored out and gone over here. So even if I didn't do that, I mean, there was no reason why I necessarily had to separate that. I separated for aesthetic reasons, really. Because the sine series started at 1, the cosine series started at 0. So I separated the 0 case just to make it look nice. But the 0 case, the 2L part would be the component that comes out and makes the A0. And that's kind of why I put A0 over 2, because I know there's going to be a factor of 2 appearing at some point. But that's that. Next time we'll actually use that to compute some Fourier series and talk about the properties and behaviors of Fourier series.
Are we going to have to use the piecewise functions for anything other than conceptualizing why we're doing what we're doing?
Oh yeah, no, even your answer in computer, you'll see piecewise functions.
Okay, so we're going to express our answer in
Yeah.
piecewise?
Because you're having trig functions, so there are times when a cosine behaves like this some of the time,
Okay.
right? So if your answer comes up like a cosine n pi, that automatically splits into 2. If n is even, you get a positive 1 as the answer. If your n is odd, you get a negative 1 as the answer. So you immediately split into a piecewise function.
Oh,
It happens very often, the
I see.
piecewise function idea. Which is why I decided to go through it, because you're going to have to remember how to manipulate it.
Thank you, Jhevon.
Anyway, we'll stop there. We'll pick up with some concrete examples next time. Huh?